Operations Execution. In this unit, we will review operations execution. We start with a discussion on capacity management over different time frames, along with the metrics used to measure capacity. Demand management will be reviewed, including bottleneck and break-even analysis. Next, we will discuss lean operations, including the implementation of just-in-time inventory and reduced process variability. This discussion will also include the impact of lot size reduction. Capacity is defined as the number of units that can be stored, received, or produced in a given period of time. Capacity defines the cost to produce items and whether customer demand can be met. Capacity is planned over different time horizons. Long-range planning is focused on modifying capacity, including the acquisition of large equipment, facilities, and even competitors. Short-range capacity planning drives effective use of existing capacity. Intermediate range planning spans both strategies. Design capacity is the theoretical maximum output of a system. This level is seldom attained. Effective capacity is the expected output given the constraints of the system. This tends to be the operational goal for the organization. Utilization is the ratio of actual output to design capacity, while efficiency is the ratio of actual output to effective capacity. Note that both are based on actual output, not capacity. When we look at demand, we can have three different scenarios. When demand exceeds capacity, the manager may increase prices, schedule longer lead times, and increase capacity. If capacity exceeds demand, the manager may stimulate demand through marketing and product improvements. Finally, when dealing with seasonal demand, companies can produce complementary products or build inventory during the off-season. The service sector must also deal with mismatches between capacity and demand. Demand management may include appointments, reservations, and serving customers on a first-come, first-served basis. Capacity may also be addressed through the use of temporary staff and variable shifts. A bottleneck is that part of the process that is the slowest or has the lowest capacity. Think of a garden hose with a kink in it. The flow of water can be no greater than that through the smallest hose cross-section. The goal of bottleneck analysis is to analyze the process from beginning to end to find the bottleneck process. Effort would then be taken to address the bottleneck by improving its capacity and throughput. Note the difference between cycle time and process time. Here we see a process flow diagram with three processes in series with two queues to isolate them. We see that process B is the bottleneck since it takes the longest time per unit produced. Process B cannot keep up with the product created by process A, while process C will regularly have to wait for process B to produce more material. The throughput time in this example would be 2 minutes, plus 4 minutes, plus 3 minutes, for a total of 9 minutes. The bottleneck is the toaster. By replacing the current manual toasters with a conveyor toaster, we reduce the toasting process to 20 seconds. The bottleneck is now the wrapping station. Wrapping would offer our next best opportunity for throughput improvement. Analyzing the capacity, we see that with a new conveyor toaster, we can produce 96 sandwiches per hour with a throughput time of 142.5 seconds. Another method for evaluating a process is through break-even analysis. We start by estimating fixed and variable costs along with revenue. The break-even point is the point in dollars and units where cost equals revenue. Depreciation, taxes, debt, and mortgage payments are examples of fixed costs, where the cost is independent of the unit volume produced. Variable costs are costs that vary with the number of units produced. Examples include labor, materials, and utilities. Total cost is the combination of fixed and variable costs. Contribution is the difference between the price and the variable cost. The line representing revenue starts at the origin and proceeds upward with a slope equal to the selling price of each unit. The break-even point is where the revenue and cost lines cross. When managing capacity, there are three general strategies: leading demand, lagging demand, and straddling demand. Leading demand means always having more capacity than needed. The customer is never disappointed. When lagging demand, you are constantly catching up with your demand, and the customer is often disappointed, but your costs are lower. You have the option of adding capacity in smaller or larger increments. Finally, some organizations adopt more of a 50-50 approach, where you are leading part of the time and lagging the remaining time. Lean operations are all about reducing waste. The customer gets just what they ordered with no excess cost, material, or labor. This strategy is supported by just-in-time and pull methodologies. Toyota has been the breeding ground for quality and process innovation for years. They are one of the largest auto manufacturers in the world. One key to their success has been the implementation of just-in-time and total production system. For just-in-time to work, the team must work constantly to improve the process and eliminate the issues that prevent the smooth flow of material. The result is the creation of vehicles with high quality and lower cost due to minimal assembly time. Here are the elements of the TPS system. You find optimization in all aspects of production. Hiring the best people and treating them well is foundational. The factory is level loaded with materials delivered just in time using a pull system. Standard work practices are used for consistent quality while using custom machinery to produce the best results. Processes include the use of display boards, monitoring performance, and continuous improvement. This is not a single approach, but a coordinated effort applying best-in-class techniques. How do we define waste? Waste is anything that does not add value from a customer point of view. In other words, would the customer choose to pay for it if offered as a separate option? In our previous discussion of value-added processes, we identified that storage, inspection, delay, queues, defective products, and unnecessary travel are all considered waste. Taiichi Ohno, father of the Toyota production system, identified 7 types of waste. They are shown here. This list is a great starting point when identifying waste in an operation. Overprocessing is adding more value to a product than the customer requires. This waste is controversial, as it suggests that it is wasteful to give a customer more than they paid for. Stable processes are important for customer quality, productivity, and minimal cost. Eliminating variability helps you achieve this goal. Inventory is often used to hide variability. Excess inventory builds a buffer between processes that are not in alignment or have excess variability. Inventory is often used to hide problems in the process. Variability in process performance is often the problem. If process activities can be predicted consistently, the process design can adapt. However, with variability, the process is in constant turmoil. This diagram depicts variability as rocks in the water that the sailboat must avoid. As long as we have sufficient inventory, the boat sails smoothly, ignorant of the rocks hiding beneath the surface. But as inventory is reduced, shown as a lower water level, the rocks are exposed. Now that the issues have been identified, employee teams can address the identified issues and reduce variability. Once these issues have been resolved, the inventory or water level may be reduced again, identifying additional issues to be addressed. This technique is often used by companies attempting to reduce their inventory levels. Inventory may be lowered temporarily to identify issues. The inventory may then be increased to ensure business success while the issues are addressed. The levels are then reduced again to determine if the action plans have been successful. Ultimately, when all process variability has been reduced or eliminated, the inventory or water level may be reduced to a level that minimizes carrying cost while ensuring business success. Combining lean and just-in-time is a powerful strategy, but requires a strong relationship with suppliers. The result can be reducing waste and increasing throughput. Implementing a just-in-time methodology can create a competitive advantage. This list displays many of the potential outcomes. Key results include improved quality, reduced cycle time, stronger supply chain relationships, more accurate schedules, and a flexible, empowered workforce. Typically, we think that improved quality and reduced cycle time increase cost. However, the ultimate result of just-in-time methods is a faster response to the customer at lower cost and higher quality. To make just-in-time methods possible, strong supplier relationships are required. The goal is to create a partnership where both companies can work together to streamline processes, reduce inventory, improve quality, and reduce response time. As in any partnership, both parties, the buyers and the suppliers, share the tasks necessary for success. Risk is involved on both sides, such that mutual understanding and trust are required. Both parties are sharing information that would traditionally be considered a trade secret or for internal use only. The risks to suppliers are numerous. One of the greatest long-term concerns is diversification. Partnerships often evolve to a point where items are single-sourced. Business issues with the buyer can have a major impact on suppliers. It is not uncommon for a bankrupt buyer to take suppliers with them into economic ruin. In addition, the two companies must be in alignment regarding quality, lead times, and expenses. This graph depicts inventory quantities over time. The sawtooth is an idealized view where 200 units are ordered and placed into inventory. This is the vertical spike in the line. As material is consumed by the process, we see a gradual drop in inventory until the next shipment arrives. Ideally, the next shipment arrives just as the inventory is depleted. Since we have a triangle, the average inventory is simply half the height of the triangle. Thus, if the order quantity is 200 units, the average inventory is 100 units. A direct method to reduce inventory is to reduce lot sizes. By reducing the order quantity to 100, the average inventory is reduced to 50 units. The average inventory is proportional to the average cost of inventory. Just-in-time methods would have an ideal lot size of 1 unit. Due to a number of realities, this is not always possible. We can calculate the economic order quantity, or EOQ, to balance the various production inputs. As with most equations, we determine the given values and determine the unknown. For example, with an annual demand D of 400,000 units, a desired order quantity Q of 200 units, and an annual holding cost H of $20 per unit, we can determine the setup cost. The equation determines that the setup cost will be $1 per setup event. Since labor costs are $20 per hour, the setup time is determined to be 3 minutes. To reduce lot sizes, reduce setup time and setup costs. Setup can be simplified by pre-planning cutover activities, implementing advanced automated processes, and eliminating setup altogether by using more universal processes. This is a graphical representation of the EOQ equation showing the impact of reduced setup cost on lot sizes and cost. Reduced setup time results in reduced lot size and reduced cost. Lean scheduling brings all members of the supply chain in alignment and includes frozen schedule of small batches of material with demand based on a pull system based on need. Here we compare a just-in-time approach with large lots. Note that it takes longer to get the third product C built. This advantage has a cumulative effect if multiple processes are required in series. The Kanban method is a just-in-time method originating at Toyota in Japan. A signal of need at a later process places demand upon a previous process. Material is pulled through the process until the final product is delivered to the customer. Here we see another example showing the flow of material from component suppliers through to fulfillment of the final customer order. Each stage loads demand upon the previous group as local inventory of work-in-process goods is depleted. Key points to remember. Capacity management is performed with short, intermediate, and long-range plans in mind. Each time frame requires different actions and management overview. Longer-range plans like factory expansion are usually the most expensive and require careful planning. To manage capacity, it must be measured. Design and effective capacity are the theoretical and practical expected levels of output. Utilization and efficiency measure the actual performance of the operation. Demand is managed for both products and services to balance customer needs with operational capacity. Bottleneck analysis finds the weakest link in the production chain by finding the process with the lowest throughput. The overall operation is only as fast as the bottleneck. We focus our improvement efforts on the bottleneck. Another method to define capacity plans is through break-even analysis. This is the production volume where the operation is profitable. Lean operations are based on the original TPS that drove out waste in the operation. Waste comes in many forms, including material scrap, time, and ability. To be successful, variability must be reduced to streamline the process and reduce needed inventory. Just-in-time methods minimize in-process inventory and require strong supplier partnerships. Kanban pull methodologies are deployed to drive production based upon downstream demand rather than planned forecasts.